Hey everyone, and welcome back to part 2 of our NIST PQC series. I'm Surbhi Singh, Senior Consultant at Encryption Consulting. In part 1, we covered the core standards MLKEM for key exchange and MLDSA for digital signatures. Today we'll cover the alternatives and practical application. We're diving into SLH-DSA, the hash-based signature, and the new code-based scheme HQC. After those deep dives, we'll discuss the decision matrix, which breaks down the complex PQC math into the practical trade-offs you need for your organization. We've attached more resources for you in the description, so let's begin. Let's start with the first deep dive on FIPS 205, or the Stateless Hash-Based Digital Signature Standard. We'll unpack SLH-DSA, look at why it was standardized, and review the technical requirements for building it securely. Let's now address our final primary standard, FIPS 205. This introduces SLH-DSA, or the Stateless Hash-Based Digital Signature Standard. This algorithm is fundamentally important, not for its speed, but for its security aspect. SLH-DSA is designed to be a strategic backup to our primary lattice-based signature, MLDSA. It fulfills the critical requirement for cryptographic diversity. And this is important because SLH-DSA uses a completely different mathematical foundation that relies entirely on the proven strength of cryptographic hash functions such as SHA-2 and SHAKE. This foundation provides a high degree of long-term assurance. If a vulnerability were ever found in lattice math, our hash-based signatures would remain secure, providing an essential safety net for long-lived, high-value data. The stateless aspect of SLH-DSA is a key security feature. Unlike earlier hash-based schemes, SLH-DSA does not maintain any state information between signing operations. This is a critical design choice because it eliminates the well-known security vulnerabilities that are associated with stateful schemes, vulnerabilities that could lead to complete private key compromise if misused. Furthermore, as with all robust signatures, FIPS 205 provides the critical guarantee of non-repudiation, ensuring that a signatory cannot easily deny having created a valid signature. The standard provides extensive flexibility with 12 approved parameter sets. These sets allow organizations to fine-tune the algorithm based on their specific needs, including the chosen hash function and security level. SLH-DSA also offers two clear optimization goals denoted by S and F. S for smaller signatures and F for faster signing. This ensures that while it is generally slower than MLDSA, you can still select an implementation that best suits your environment. The stateless hash-based digital signature algorithm provides quantum-safe security, and its brilliance lies in 6 critical interconnected design principles. The hypertree is SLH-DSA's master architectural solution to the problem of key reuse, which is fatal to older hash-based signatures. The hypertree is not a single structure, it is a tree of many smaller trees. The architecture is built with multiple layers of XMS S trees stacked on top of each other. The root of a signature tree on a lower layer is always signed by a key on the layer directly above it. This chaining process continues up to the final topmost root, which is the master public key. The layer design creates a virtually infinite supply of signature positions. Because the key supply is so vast, the system is stateless. It does not need to store any internal state, such as a counter, to track which key was last used. The signature itself contains all of the necessary location data, guaranteeing that a key address is never accidentally reused, regardless of system restarts or crashes. The forest of random subsets, or FORS, is the efficient component responsible for linking the message to the signature scheme. A FORS key consists of a forest of multiple small independent Merkle trees. The process begins when the message digest is broken down into several smaller pieces. Every piece of the message digest acts as an index, selecting one specific secret value or leaf from one of the small trees in the forest. The FORS signature includes all these selected secret values along with the proof required to link them back to the root of the respective small tree. All the roots from the forest are then combined and hashed into a single FORS public key. It is this single public key that is then passed to the hypertree to be signed, finalizing the link between the message and the scheme's master public key. The security of SLH-DSA rests on the difficulty of breaking hash functions, but the system practices strict domain separation. It relies on 6 specialized hash function variants derived from the same base function. Each variant has a dedicated fixed purpose. Some are exclusively for building the tree structure, one variant is only for deriving secret keys from the master seed, and a separate function is used only for randomizing the message digest. By assigning these unique roles, the algorithm ensures that data from one security domain, like key derivation, cannot be confused with or maliciously substituted into another domain, like node hashing, even if the input and output sizes are identical. This compartmentalization is an important security feature. This is a crucial defense against cryptographic attacks. Every single hash operation within the entire hypertree must be accompanied by a unique 32-byte address or ADRS, which acts as a context identifier. The ADRS is a structured data containing coordinates, the hypertree layer, the specific tree's identity, and the height and index of the node being computed. By forcing the ADRS to be a part of the hash input, the system ensures that no two hash calls will ever have the exact same input across the entire scheme. This cryptographic binding of data to its location prevents multi-target attacks where an attacker attempts to use a valid hash from one point of the algorithm to forge a signature in another part. The algorithm provides two distinct modes for incorporating randomness during the message signing process, offering a balance between security and predictability. The hedged variant is the default and most secure mode, designed specifically to counter side channel attacks. Before the message is hashed, a secret key generates a fresh, unique random number which is included in the signature. This randomizer is mixed with the message digest input. Since R is new every time, the internal execution path and resulting message hash are constantly randomized, making it extremely difficult for an attacker to extract secrets by analyzing physical properties like power consumptions. The deterministic variant is an option for testing on or environments that lack a high quality random source. This mode uses a fixed publicly known value in place of the fresh random number, ensuring that signing the same message always produces an identical signature. The security model protects the master private key by splitting its function between two separate seeds, ensuring a compromise of one does not invalidate the other. The key is divided into the master builder seed, which is used exclusively to pseudo-randomly derive all the temporary secret keys for the FORS and WATS plus components across the entire hypertree, and the randomizer key, which is used only for generating the random number R for message hashing. This strict isolation means that if the randomizer key is ever compromised, the master builder seed remains secure. This compartmentalization limits the potential damage of any single leak, enhancing the overall security of the entire signature structure. Now we look at the parameter sets for SLH-DSA, or hash-based signature backup. This is a very different story from MLDSA. While MLDSA balances speed and size, SLH-DSA forces a much sharper trade-off: speed versus signature size. NIST approves 12 parameter sets for SLH-DSA, and they are organized by two critical optimization goals: S for small signatures, and these sets minimize the resulting file size of the signature, making them ideal for systems where bandwidth or storage is limited. F for fast signing, and these sets prioritize speed, making the algorithm sign the document quicker, although the resulting signature file will be much larger. When you choose a parameter set, you're essentially choosing between these two performance priorities. The 12 sets cover all three main security categories, aligning with AES 128, AES 192, and AES 256 levels. But look at the practical implication of the size trade off. At the lowest security level or category 1, the S version produces a signature of about 7,800 bytes. If you switch to the F version for faster signing, that size more than doubles, jumping to over 17,000 bytes. This dramatic difference is why SLHDSA is considered a specialist tool. The signatures are significantly larger than those produced by MLDSA, but we accept this cost because we are getting greater security based purely on the rock solid strength of SHA-256 or SHADE-256. Finally, every parameter set gives you a choice of hash function. You can use the older, well-vetted SHA-256 or 512 or the newer, more modern SHADE-256. This choice, along with the optimization goal, allows us to precisely tailor the strategic backup to fit the specific needs of our environment, ensuring it delivers the required security at the minimum acceptable performance impact. SLH-DSA's biggest advantage is its foundation. While MLDSA relies on the new and powerful lattice math, SLH-DSA security is built on something we've been using for decades, cryptographic hash function like SHA-2 and SHAKE. This gives your business crucial cryptographic diversity. If a weakness were ever discovered in lattice-based signatures, SLH-DSA would be your backup plan. Its security relies on the well-understood and time-tested hardness of hash functions, which have been studied by cryptographers for decades. This provides a high degree of long-term assurance and confidence in its resilience. A major innovation of SLH-DSA is that it is stateless. This is a huge benefit for businesses, particularly for large-scale applications. Some older signature schemes require you to keep a track of a state or how many times a private key has been used. If you lose track of this state, you risk reusing the key and completely compromise your security. SLH-DSA solves this problem. It doesn't require any state management between signature operations. This eliminates the risk of private key reuse and makes your key management far simpler, more scalable, and less prone to human error. It's a perfect fit for environments like PKIs where statelessness is an essential operational requirement. While generally slower than MLDSA, SLHDSA has been meticulously optimized to meet security requirements of organizations. The standard offers flexible parameter sets with distinct design goals. You can choose a version optimized for smaller signatures denoted by an S, which is perfect for bandwidth constrained environments, or you can choose a version optimized for faster signing denoted by an F to prioritize speed. Additionally, SLH-DSA's public keys are comparatively small, which can be an advantage for resource-constrained environments. And like all good signature algorithms, it provides non-repudiation, ensuring a signatory cannot easily deny having created a signature. In summary, SLH-DSA is a strategic and flexible standard that offers a different path to post-quantum security, providing your business with diversity, simplified management, and a robust, proven security foundation. SLH-DSA is an incredible piece of engineering. It's our defense against quantum computers trying to break our digital signatures. But even the best algorithms can be defeated by a tiny flaw in the code. So, for the engineers building the system, they must follow these 6 critical implementation requirements. Think of these as the 6 essential rules for creating a truly secure cryptographic module. The first is the segregation mandate. This is all about maintaining strict cryptographic boundaries. The first rule is the key you use for signing must not be used for anything else. You can't use it for encryption, key exchange, or any other protocol. And why is that? Because if a hacker finds a tiny weakness in your encryption system, we don't want that to automatically compromise your most valuable asset, which is the key you use to sign for authenticity. The second part is the black box rule. The signature code has to be sealed off. The main software you can say, please sign the document, but it can never reach inside the module to touch the private key or manipulate the internal calculations. Security is all built on unpredictability, and that's where our second point comes: the purest randomness mandate. When the SLH-DSA key is first generated, it needs several massive secret numbers, and we call them seeds. The core requirement is that these seeds must be fresh, never used before, and they must come from a NIST approved random bit generator. If we use a cheap, predictable random number generator, it would be like hiding a secret in a location a hacker already has a map for. By mandating the highest quality entropy, we ensure the random source is absolutely unguessable, which is the ultimate source of security for the entire system. Next is the instant erase mandate. This rule defends against hackers who try to snoop around after the signature is created. The second the program is finished with a piece of sensitive data, whether it's a private key itself or just a temporary value from an intermediate hash chain, it must be instantly and completely scrubbed from memory. This is formally called zeroization. It's like having a whiteboard that gets instantly wiped clean. If a hacker tries to peek into the machine's physical memory right after a signing operation, they won't find any residual data crumbs that could reveal the secret key. Next is the Approved Tools mandate. It ensures trust and interoperability across all certified products. The SLH DSA algorithm is constructed using smaller, powerful cryptographic tools, primarily the hash functions. The rule is that engineers must only use the hash function explicitly approved by NIST for the standard, like the specific options of SHA2 or Shake. You can't use a custom hash function and you can't use an old deprecated one. This mandate guarantees that the system's foundation is built on rock solid, well studied primitives, and it ensures that a signature created by one compliant device can be verified correctly by any other compliant device. Our second last point is the integer math mandate. This is a rule of absolute mathematical correctness. The implementation must use only whole numbers or integers for all cryptographic math. Floating point numbers, decimals are strictly forbidden. And that's because floating point operations can introduce tiny, unpredictable rounding errors depending on the specific hardware. In a digital signature, even the smallest error in calculations means the signature verification will fail. Using only integer math guarantees a perfectly predictable and consistent result across every single certified device, which is essential for integrity. And our last point is the side channel guard mandate. This is arguably the most challenging and important rule for hardware engineers. Your implementation must be engineered to protect against physical espionage. We're talking about timing attacks and fault injection attacks. You must ensure two things. First, the time and power it takes to sign a document never changes based on the value of the secret key being processed. This is constant time execution, which defeats an attacker measuring tiny physical differences. Second, the code and hardware must be resilient against external interference that hackers use to intentionally corrupt the module and force it to leak secrets. This rule ensures that a perfect algorithm isn't just broken because the physical device betrays the secrets within. Great. Now let's pivot for an in-depth look at HQC. We'll move beyond the standardized algorithms to explore the unique security and performance properties of this code-based encryption scheme. We have talked a lot about MLKEM, the primary key encapsulation mechanism or KEM that NIST has already standardized. MLKEM is fast and efficient and it's a go-to for post-quantum encryption. But we need to address a fundamental question of long-term security. What if you're wrong? The primary algorithms MLKEM and MLDSA are both built on lattice math. If a major flaw or a genius breakthrough were to ever crack lattice cryptography, it would compromise every single system relying on those standards globally, and that is a massive systemic risk. That's where HQC comes in. NIST selected HQC specifically to be our designated secondary KEM, our high security standardized safety net. Its entire purpose is to provide cryptographic diversity, ensuring that if the lattice-based system fail, we have a fully vetted different type of defense ready to swap in immediately. HQC security doesn't rely on the geometry of lattices at all. It's built on a completely different branch of mathematics, which is the error correcting codes. These are the principles that are used for decades in everything from deep space communication to your internet connection to fix garbled or noisy data. The core security principle in HQC is the difficulty of decoding a random linear code. Think of it this way: when you encrypt a key using HQC, you're introducing a very specific, carefully controlled pattern of errors into the data. The receiver holds a private key or a secret decoder book that allows them to efficiently locate and correct those precise errors, revealing the original secret key. Without that secret decoder book, trying to guess the original key is computationally impossible even for quantum computers. This code based foundation provides an uncompromised line of defense that is mathematically distinct from lattices. Like all KEMs, HQC performs the three basic functions of public key encryption: key generation, encapsulation, and decapsulation. Its output is a highly secure, fixed length shared secret key, which is then used by symmetric algorithms like AES to encrypt your actual data. HQC also offers a range of parameters like HQC 128, HQC 192, and HQC 256, allowing organizations to select the security strength that matches their highest needs, all the way up to the quantum equivalent of AES 256. Now, let's be realistic about the trade offs. The high assurance mathematics of HQC comes with a cost. Compared to the highly optimized MLKEM, HQC is generally slower and has larger key and ciphertext sizes. This means it consumes more computing power and requires more bandwidth. HQC is not designed to be the fastest algorithm. It's designed to be the most secure backup. Its clean, secure operation convinced reviewers that its diversity benefits outweighs those resource costs. While MLKEM is already finalized, HQC is progressing through the final phase of the NIST process. It was selected for standardization in 2025. We expect NIST to publish the official draft standard next year in 2026, which will detail all of the technical requirements. The finalized standard is anticipated to be published around 2027. This timeline is important. It gives our engineering teams the time they need to not only fully implement the primary MLKEM system, but also to build the necessary crypto agility into our infrastructure. The goal is to ensure that if the unthinkable ever happens to lattice cryptography, we can rapidly switch to those code-based security of HQC with minimal disruption. Now let's focus on the HQC algorithm and the 6 key design features and competitive advantages that led to its standardization by NIST. This is a look inside the strategic engineering that defines its security. The first principle is strategic: security diversity. Since the current primary standard MLKEM relies on lattice problems, HQC was required to provide a completely different defense. HQC achieves this by grounding its security in error correcting codes, specifically the difficulty of the quasi cyclic syndrome decoding problem. This strategic separation is important because it ensures that a single breakthrough in one area of quantum mathematics won't compromise all key establishment protocols simultaneously. The single element was the single most decisive factor for NIST. For any key encapsulation mechanism to meet the highest security standard, it must have a reliably proven extremely low decryption failure rate. HQC provided a mature, stable, and theoretically justified analysis of its DFR that consistently met the security thresholds. This contrasts sharply with its rivals whose DFR analyses were considered less mature and potentially required complex, undesirable workarounds to ensure security. HQC's stable analysis proved its inherent security confidence. HQC offers a distinct speed profile that is highly beneficial to the receiver. While it may not be the fastest at every step, it excels at the two operations that are critical for performance. Key generation is significantly faster, 6 to 10 times faster than its main competitor, and decapsulation, the critical decryption step, is 5 to 7 times faster. This superior speed on the receiving end is a major operational advantage for any server handling frequent decryption tasks. HQC's internal design ensures its security proof is both direct and clean. The algorithm was built with a direct security reduction to the QCST assumption. A key design feature is that the security analysis is independent of the specific decoding algorithm that is used for decryption. This inherent structural stability, where the code's hidden structure is separate from the secret key generation, simplifies the entire security argument, increasing confidence in the scheme's long term robustness. While HQC is not the smallest algorithm, its keys and ciphertext are larger than some competitors, and its overall profile was deemed perfectly acceptable for the majority of general applications. Its higher processing speed compensates for its large size. The successful navigation of the trade off prioritizing speed and security confidence over minimal bandwidth makes HQC a viable solution for widespread use. Finally, a non technical but essential building block is the freedom to adopt the algorithm. The HQC submitter secured a formal commitment from the patent owner to grant a non exclusive compensation free license to anyone implementing the standard. This guarantee removes a critical legal barrier, ensuring HQC's global deployment can proceed quickly and without any restriction. These six building blocks, from security, diversity, and stability to speed and legal certainty, are why HQC was chosen. It provides the stable, fast code based standard necessary to compete a comprehensive and resilient quantum safe defense portfolio. Now we look at HQC, which is critical because it's the algorithm NIST selected to provide cryptographic diversity alongside the lattice based MLKEM. HQC security is based on error correcting codes, meaning its security is completely independent of the lattice schemes. Like MLKEM, HQC provides three parameter sets aligning with familiar security levels HQC 128, HQC 192, and HQC 256. However, HQC has a very distinct performance profile compared to the lattice algorithms. The numbers here reflect its unique trade offs, particularly when compared to its primary competitor, Pike, and the ubiquitous MLKEM. Let's look at the key sizes. Notice a remarkable feature: the size of the secret decapsulation key is a tiny 40 bytes across all three security levels. This is a huge benefit for systems with private key storage limitation. In contrast, the public key and ciphertext sizes are noticeably larger than those produced by MLKEM. For the highest security tier, HQC 256, the ciphertext size is about 14.5 kilobytes. This makes HQC more bandwidth intensive. So, HQC has a profile of small secret keys, large public data, and fast processing. This leads to a specific deployment implication. Benchmarks show that when network latency and packet loss are low, HQC tends to result in faster overall handshakes than other code based candidates because its actual processing time is faster. However, because its ciphertexts are large, when network conditions are poor with high packet loss, HQC's performance can drop as the larger data size is more sensitive to retransmission issues. In summary, HQC gives us the crucial benefit of code based diversity with a performance profile that favors fast processing over small bandwidth. This makes it a robust complement to MLKEM, ensuring our security is not tied to a single mathematical assumption. HQC isn't about replacing MLKEM, but about giving your business an important second line of defense. Think of it as a cybersecurity insurance policy that is protecting you from risks that you can't even foresee yet. In a world of investing, we're taught to diversify our portfolio to protect against a market crash. The same principle applies here. By using a different mathematical foundation, HQC provides an important plan B for organizations. If a quantum computer or a new mathematical discovery were to ever suddenly find a weakness in all lattice based cryptography, HQC would remain secure. This gives your business crypto agility, the power to switch to a different standard and protect your data from a threat no one saw coming. It's the strategic choice that ensures you are never reliant on a single type of cryptographic solution. HQC security is not just theoretical, it's based on decades of research. The underlying mathematical problem known as the syndrome decoding problem is one of the oldest and most well-studied problems in coding theory. This isn't a new unproven theory. After decades of research, including scrutiny from the world's best cryptographers, there are no well-known efficient quantum algorithms that can solve this problem. This history of resilience gives HQC a degree of long-term assurance and makes it a trustworthy choice for data that needs to remain secure for years or even decades. Some people might hear about HQC and worry because it uses a probabilistic process, but for all practical purposes, this is a non-issue. HQC has been meticulously engineered to have a decryption failure rate that is so incredibly small, it's statistically impossible to encounter in the real world. We're talking less than 1 in a million times. This means you can integrate HQC into your systems and operate with the same confidence as a deterministic scheme. You get all the benefits of cryptographic diversity without any operational risk, ensuring your communication will never fail unexpectedly. HQC proves that you can have both a diverse cryptographic portfolio and a reliable practical system. It's security without compromise. Up next, we are moving from the code requirements to real world deployments. We'll be discussing the decision matrix, which breaks down the complex math behind the new PQC algorithms like MLDSA and MLKEM into practical trade offs you must consider for your organization. We've seen the threat, the quantum computer is coming, but let's move past fear and focus on action. We have the new NIST standards, and the biggest question is which one should we use? The answer entirely depends on your specific requirements. Let's break down the trade offs into three simple categories. Our first factor is performance, or simply put, speed. The great news is that PQC is not a sacrifice. The fastest algorithms are built on lattice math, which runs incredibly well on today's CPUs. Our go-to standard for speed is dilithium for signatures and MLKEM for key exchange. In test, dilithium is actually faster at securing connections than the old RSA 4096. This means we get quantum security and better speed. However, there's a catch. Verification is harder. When a server checks a new certificate, say a certificate authority, or a web server checking thousands of users, the process is slower than with RSA. And that is our biggest operational hurdle. If you run a high traffic server, you need to budget for CPU optimization to handle this new verification load. A second factor is bandwidth or size. If you're running a massive data center, you want the fastest processing of dilithium, but if you're building something for a constrained environment like an IoT device, a mobile app, or a slow connection, you want the smallest possible data size. That's where Falcon steps in. Falcon is the specialist. It's engineered to produce the absolute smallest signature and certificate sizes of all the quantum resistant algorithms. It sacrifices a tiny bit of processing speed, but in return, your data can often fit into a single network packet. So the decision is clear. Dilithium for CPU bound speed and Falcon for network bound speed. Finally, we have security assurance, which I like to call the backup plan. If all our fastest algorithms, dilithium, Falcon, MLKEM, rely on the same lattice math, what happens if quantum scientists break that one type of math? The answer is everything fails. To prevent this catastrophic single point of failure, NIST gave us diversity. They selected two independent algorithms as your safety nets. Sphinx is a signature based on fundamental hash functions, the most conservative, reliable type of math we have. It's slow and produces huge signatures, but its security is completely independent. HQC is a key exchange based on error correcting codes, providing a non lattice backup to MLKEM. The strategy isn't either or, it's both. Use the fast lattice schemes for your high volume daily transactions, but use the diversity schemes for securing your most valuable assets like root keys that must last for decades. The PQC standards are finalized. They're faster than their classical predecessors and they offer unprecedented mathematical diversity. Your next stops are to move beyond pilot test and start planning your hybrid deployment. Choose the right tool for the job. Dilithium for speed, Falcon for size, and Sphinx and HQC for defense in depth. This section is all about how we can help you in your PQC journey. We'll explore our service, expertise, and solutions that are available to guide you through every phase of this critical PQC migration. Now, let's talk about how encryption consulting can help you make a seamless and strategic transition to post quantum cryptography. Our approach is designed to minimize disruption, strengthen compliance, and keep your cryptographic environment resilient against emerging threats, both today and in the quantum future. We break this journey into three key pillars. Risk assessment and gap analysis is where it all begins. We start by applying a customized PQC readiness framework to evaluate your current cryptographic environment, including protocols, systems, and assets. We conduct crypto discovery to map out exactly where and how cryptography is used. Then we identify vulnerabilities, especially those exposed to quantum risk, assessing which systems will need to move to new standards like MLKEM for key exchange or MLDSA and SLHDSA for digital signatures. Finally, we deliver a detailed gap analysis report aligned with NIST standards with clear actionable recommendations. Strategy and roadmap is where we help you build a tailored PQC migration strategy that fits your business goals. This includes defining a crypto agile operating model and outlining a detailed milestone driven roadmap for PQC adoption. We help you select the optimal PQC algorithms, whether you need the fast performance of MLDSA or the unique properties of SLHDSA, and incorporate leading industry practices to ensure your environment is not just quantum resistant, but agile and adaptable long term. And of course, our experts provide hands on consultation throughout the planning phase. Finally, we help bring the plan to life. We support hybrid implementations to ensure smooth coexistence between classical and post quantum systems. We also help develop crypto agile environments, retire insecure algorithms, and ensure compliance with NIST PQC standards. And once deployed, we stay involved, continuously monitoring and maintaining your cryptographic ecosystem. So, whether you're just starting your PQC journey or already planning migration steps, EC brings a structured, proven approach to help you reduce risk, maintain compliance, and build future ready cryptographic infrastructure. Thank you for joining us today. This transition to post quantum cryptography is not just an upgrade, it's an investment in your organization's longevity and trust. So stay tuned as we release more videos as part of our PQC series diving into more details on these critical topics. If you want to reach out now or learn more about anything that we've discussed today, you can drop us an email at info@encryptionconsulting.com or visit our website at encryptionconsulting.com. We look forward to partnering with you on your quantum safe journey. Thank you so much.